Well, good afternoon. I'd like to present to you some work I did with my colleagues Stuart Glynn and Tony Richards. Gallium nitride technology, I'm sure you've all heard of gallium nitride. It's got proven capabilities for high power amplifiers. Now, a lot of the early applications of gallium nitride, they focused on high levels of saturated power. In fact, people seemed to go out the way to develop as much saturated power as they could. And it is a more expensive technology than gas or in silicon. And people would tend to bolt a gallium nitride booster on the output of an existing solid state PA, or sometimes they'd bolt a gallium nitride amplifier on the input of a TWT. And it was all about saturated power. However, as the technology has matured, things are moving on. And gallium nitride is increasingly adopted for high linearity applications. Probably the most well-known is base station power amplifiers. And there's a lot of work underway now with people developing gallium nitride transistors to replace the current LDMOS transistors. And even Freescale and NXP, the biggest LDMOS players, are both heavily investing in the gallium nitride market. Now, I'm going to talk to you about gallium nitride PAs for line-of-sight link applications. And this is a market which is currently dominated by gallium arsenide. We're going to start by looking at an example, a PA for 15 gigahertz line-of-sight links. And this is a European band. There are various bands from around about 6 gigahertz up to 40 gigahertz. We're going to develop this PA using Cree's quarter-micron GaN and silicon carbide process. The initial design will optimize for the conventional measure of linearity, third-order intermodulation point. But that's not what is really important for a line-of-sight link. What's important is that when you amplify a complex modulation spectrum, that you preserve the modulation fidelity. So we're going to pass QAM 256 through that PA and look at the sort of degradation we see. We'll look at spectral regrowth, the adjacent channel power ratios. We'll look at the constellation diagrams and the error vector magnitude, which is a well-used metric for constellation distortion. And we'll look at how these parameters vary with the bias of that amplifier. So this was the initial target specification of our PA. So the frequency range of 14.5 to 15.35, and this is the so-called 15 gigahertz point-to-point band. A gain of something greater than 20 dB. It's going to be a packaged IC, and a gain of 20 to 25 dB at microwave frequencies is a sensible level for a packaged IC. Output IP3, we were aiming for 45 dBm at 22 dBm of output power. Now, one of the reasons for looking at gallium nitride is to increase this IP3 level. And the reason we want to increase the IP3, we're not looking to generate more output power in actual fact than the incumbent gas solutions. We're looking to have better linearity so that we can up the level of the modulation, the order of the modulation. QAM 256 is now routinely used. QAM 512 and 1024 is being rolled out, and people are investigating higher order modulation schemes. Now, as you'll see, as you go higher and higher, all of the constellation points get closer and closer. You can upset that constellation with a much lower linearity, a much lower level of distortion. So you need much higher levels of linearity in order to amplify it. The saturated output power, 38 dBm, and PAE for the whole amplifier of 35%. And one other important point, a lot smaller area than gallium arsenide parts. Now, GaN per millimeter squared is more expensive than gallium arsenide. However, the power density of GaN is higher, so you can get a smaller chip. We're using the Cree quarter micron GaN on silicon carbide process. We're going to bias it up at 28 volts VDS, and at the frequency range we're operating, it has about 4 watts per millimeter of RF output power. This is one of the transistors, and it has these inter-source vias, and these are nice for keeping down the source inductance, which helps preserve the available gain from the transistor at the higher microwave frequencies. They also spread the gate fingers quite nicely, which is important for thermal operation. And that gives you this wide gate pitch here. The PDK that Cree supply is nice. It's got a facility in it to predict the thermal effects of on the RF performance. You have to put in the thermal impedance of your transistor, which is down to the designer to work out, so it does require some skill. But given that, if you type in the base plate temperature, then the model will tell you how the performance varies due to the self-heating effects. Now, using these models and our CAD simulators, we can tell you exactly what the RF voltage is here and the RF voltage is there. But it's only going to be accurate if the models are accurate. And this is something Rob touched on in his presentation. Your design is only going to be as good as your models. Another important note, good thermal design is critical in all ICs, but it's very critical in GaN. People tend to overlook it. Now, we've got a high power density, 4 watts per millimeter. That also means we've got a high level of power dissipated in a small area. Now, silicon carbide, the substrate for this process, that's got a great thermal conductivity. It's got a thermal conductivity better than gold. Who'd have thought it? However, this is an important point. That's at room temperature. The thermal conductivity of gold varies very little from room temperature and 200 degrees centigrade. The thermal conductivity of silicon carbide drops by a factor of 2.5. Now, if you look at data sheets for commercial devices, certainly good commercial devices, you'll see that it has thermal impedance data which varies with ambient temperature. And that's because of this effect. And it's very important to consider and understand when you're designing a gallium nitride IC, you as the designer are responsible for ensuring that the thermal performance is adequate. And if you get it wrong, then your reliability will suffer. So the preliminary design, we started out with some simulations and we looked at a 1 millimeter transistor, 4 by 250 micron. Initially, we biased out 100 milliamps. That's 100 milliamps per millimeter, obviously. And this is the classic G-max curve we see. I'm sure you're all familiar with this. This point here is where we transition from a region of conditional stability here to a region of unconditional stability here. So round about our band here, the device is unconditionally stable, which is nice, and we've got a gain of 14 dB. So we believe when we account for the matching networks, the bias circuitry, the gain flattening, the low frequency stabilization, we've got a lot of gain down here. We have to do something to make sure that that gain won't cause us problems. With all that taken into account, we should be able to achieve 11 to 12 dB of gain per stage. So we move forward with our design. We start looking at this transistor. Initially, we look at it in a 50 ohm system, and we see what we need to do in order to conjugately match it to 50 ohms. We're not going to conjugately match it, I will say that, but we start off looking at what we'll do. We'll conjugately match it, and with a 0.3 nanohenry inductor, that pretty much takes us to the 50 ohm point. This is one of gallium nitride's high operating voltage advantages. The output impedance for a certain output power is higher. This makes it easier to achieve broadband operation. And even if you don't want broadband operation, it makes the whole matching process simpler. We then undertake some load pull simulations, and we look at the load impedance we need for 3 different cases we've got here. This is for the saturated output power, and that's our optimum PSAT point, and we get 4 watts of output power, 46.8% efficiency, and 43 dBm output IP. For the 4 watts of output power. This second point, you see the optimum match point has moved slightly. This is matched for PAE. We get 46.8%. And this final plot here, we're looking at the match for best IP3. There we get 43.1 dBm at this particular bias point. And these contours here show what happens as we drop the power level dB for dB at the input. So there's a little bit more work involved, and then you end up with this. I want to present some details of the complex modulation and the effects of the PA on that. So I'm not going into huge amounts of detail in the design, but I have got a nice clear plot of the layout. This isn't what they give you on data sheets these days. Time was they used to give you a nice clear image of the IC and you could see what was going on. Now they blur it all. But this is a nice clear image. You can see we've got 2 output devices, 1 millimeter each. They're combined here at the output. This is some capacitive matching. See, we've got 2 capacitors here. We've got 2 capacitors there because that means we can use a larger capacitor, and smaller capacitors have degraded ESD performance. And the larger capacitor is also more immune to variation with process tolerance. We've got an inductor here, which is through which we're injecting our gate bias. These transistors can draw a reasonable amount of gate current, so we can't have too high a gate resistance. It's a modest gate resistance here. It's the gate bias point here, the gate bias point here. And more capacitive decoupling here. What we tend to do, this is for the lower frequency decoupling. And what we have is a resistor to a capacitor. And the whole aim of this is just to kill that gain at lower frequencies. Now, any IC shouldn't require microwave decoupling off chip. You've done something a bit wrong if it does. All your microwave decoupling, all your RF decoupling, that should be on chip. It's your low frequency decoupling you want off chip. We've got some RC decoupling here. And what we do is we tend to fill in the spaces like we've done here with this to put in as much capacitance as we can without excessively increasing the chip area. We've got a driver stage here, which it's a little bit less than 2-to-1 ratio. You have to be careful with a GaN IC of having too small a driver stage. It's a classic mistake people make who've been used to designing p-hemped ICs, and they work out the size of the driver they should use on the conventional metrics. But they end up with something too small because gallium nitride has a very soft compression characteristic. So you'll end up with a multi-stage IC that you need to drive 10 dB into saturation in order to compress it. So make sure you don't go too small in your driver stage. We have the driver stage, which we split here, and we've got low-pass LC matching. These are capacitors, these are vias, these little ellipses. And ultimately, we need to EM simulate this. It costs a lot to make ICs, and people like them to be right without having 6 or 7 runs. Ideally, we like them right on the first time. Now, what I'm showing you here is this is a commercially available gas IC. That's the outline for it. That has similar performance in that 15 gig band. Actually, it's got a couple of dB less IP3. So we've got a much smaller IC, and we've got slightly better IP3, 2-3 dB better IP3, which will mean we can push higher order modulation through that PA and achieve adequate modulation fidelity. That's what we're aiming for. This is the simulated performance of the IC. See with the gain there, we've got 22.5 dB. It's a nice broadband gain plot across our band of interest, slightly wider than our band of interest. We've got 22.5 dB of gain. This is the 3 dB compressed output point. You have to be very careful when you're looking at commercially available GaN ICs. This is my top tip for you. They have this metric PSAT watch out for how far into compression you need to drive that IC to get to the PSAT point. Some of them are fine, but some of them, you know, I've seen 10 dB. And this is our PAE here. And that's around about the 37% mark for the two-stage IC. This is our output IP3 here. And we're achieving 46 dBm at the 22 dB per tone level. So this is the simulated performance summary for our IC in the conventional microwave metrics world. So this is what we had as our target specification. So we've got that band with some guard band top and bottom. We've got a little over 22 dB of gain. Input return loss is greater than 15 dB. Output return loss greater than 14 dB. We could have achieved better output return loss. It's actually quite straightforward, but we pay for it in reduced IP3. Our IP3 at this particular bias, 46 dBm. PSAT's greater than 38 dBm, PAE 36%, and quite a bit smaller than the commercially available gas parts. And it needs to be, because the GaN parts are more expensive per unit area. What we did next is we started investigating the output IP3, how it varied with bias. Now, initially we had 100 milliamps per millimeter bias. We actually moved to 130 milliamps per millimeter bias during the design process because that gave us some IP3 advantage. What you can see here, this dark blue trace, if we go to 160 milliamps per millimeter, we get quite 3–4 dB more improvement. If we go to 200 milliamps per millimeter bias, which we're not going to do because we don't believe that is thermally judicious, you could see you get some peak in here. Again, all of this stuff is only true if you've got good, accurate models. Now, fortunately, if you go to a good foundry, they have spent a lot of time and money generating these models. They still require a lot of ingenious skill to use them effectively and get the most out of them. But you can get simulated performance that matches well to what you end up measuring. So a few words about higher order modulation. Here's a base station. Actually, it's some building with a base station on top of it. You see these, Addenbrooke's Hospital down the road. You're not allowed to use your cell phone inside of it, but they've seen fit to install tons of these base stations on the top. And they have a lot of these line of sight links. And that is doing the backhaul. So all your teenagers down in the latest tweets or the gaming apps, all of this is to cater for them. And there's tons of stuff to backhaul. All your iPhones continuously polling the network for your mapping features. All polling the network, all generated tons of traffic to backhaul. And that is why the amount of data we need to backhaul is going up, and we're being pushed up the modulation schemes. QAM 256 now, it's pretty standard to operate with 256. 8 bits per symbol. 512 is being rolled out, as is 1024. And in honesty, there looks like there's no end in sight. And moving up this modulation scheme places greater demands on the microwave front end, in particular the power amplifier, but also in the oscillators, which need very good phase noise. Here's some Constellation diagrams. This is QAM 64. You can see there's 64 points on there, 8 by 8. This is QAM 256, QAM 128, and QAM 512. And you can see they get closer and closer. In the end, there's no space between these points. It becomes desperately difficult to make sure you can discern one point from the other. Now, fortunately, our friends in the digital world introduced some clever coding schemes, which mean we can tolerate some bit errors and we can work things out. However, you do need to pay a lot of attention to preserving modulation fidelity. Here's some eye diagrams. Now, this is QAM 64. Now, here you can't see what's going on. Here you can't see what's going on. So what we have, I apologize if I'm teaching anybody to suck eggs. In the transmitter, we have a root-raised cosine filter through which we pass the data, and that helps maintain the modulation spectrum to a nice tight bandwidth. We transmit it, comes in the receiver. We have another root-raised cosine filter in the receiver. So overall, we have a raised cosine filter. And what that ensures is, at the sampling instance here, and only at the sampling instance, we have no ISI, intersimple interference. Everywhere else, these root-raised cosine filters, they actually cause intersimple interference. You can't see what's going on. Now, we have here 7 eye openings and 8 sampling instances. You need an open eye so you can tell one point from another. And you can imagine this is in the eye, and in the Q domain, we'll have another 8 sampling points here, QAM 64. And so the same with QAM 128, QAM 256, and QAM 512. And you can see they look remarkably tiny now, these eyes. Now what happens, as we'll see, when you pass this through a circuit with distortion, is the eyes start to close. This shows the modulation spectrum. This is the pure modulation spectrum, this blue trace. The root-raised cosine filtering has helped us keep this in a nice, tight, self-contained spectrum. This green trace here is the mask, the legislative mask for the class 4H transmission. And there are various other features for the transmission: 56 megahertz bandwidth, symbol rate. This is for the QAM 256 modulation, and we have a data rate of 368 megabits per second. We've normalized here to a 1 hertz scale, and if you multiply each of these by 46 megahertz, you'll get to the class 4H transmission mask. So, as I mentioned earlier, the disadvantage to the higher order modulation schemes, they're great because you fit loads of data through a small bandwidth. However, they're corrupted by the nonlinearities of the transmission system. The PA is one of the major contributors, and these nonlinearities cause closure of the eyes, and that leads to bit errors because we can't tell what bit we're transmitting, what symbol we're transmitting. And we can look at that in terms of degraded error vector magnitude. We see generation of intermodulation products in nearby channels, and that gives rise to spectral regrowth. So we see the sidebands growing and growing, and eventually they'll come up above that spectral mask. And you're obliged to meet that spectral mask. So we can predict the extent of these problems that our PA causes by using a radio system simulation. So we generate random data streams using a QAM 256 modulator. We do root-raised cosine filtering, and then we apply that signal to the PA. And we look at the PA's spectrum, the eye diagram, the constellation, and we calculate the EVM. Here's the model that we put together. Pseudo-random bit stream developed here. QAM 256 modulation, all in the digital domain here. Root-raised cosine filtering. We have a look here, another root-raised cosine filter in our receiver. And this is what we're putting in. So we can see our eye diagram, our constellation, and our spectrum. And those were all the great uncorrupted plots I showed you earlier. We adjust the drive level to set the level to what we want to go into our PA. And then we have a model for our PA, and it's a level-dependent model. And we have a a magnitude and phase transfer function of that PA, which we've generated from our circuit simulator. In this case, we used Agilent ADS, no doubt soon to be Keysight ADS. Some gain phase correction, another root-raised cosine filter, and we look at what the output eye constellation the spectrum, and the error vector magnitude. We look at what they look like there. What are we actually transmitting after our PA? So what we did after implementing this system model was to cross-check what the output IP3 performance predicted by our circuit simulator. Could we reproduce this with our system simulator? Because we should be able to. It's a simple one, just 2 tones in. If we can't do this, what chance have we got of predicting the performance with a 256 QAM modulation? Unfortunately, we could. So what we did is we generated the level-dependent amplitude and phase voltage transfer characteristics for the PA and ADS. We took them over to our Simulink simulator, and then using that system I told you, but with 2 input tones, we generated this maroon trace here. And you see it agrees very nicely with this blue trace here, which is the output IP3 versus level that we generated in ADS. And you know, this is not on extreme scale, this is quite a small scale. This is a very good agreement. So that gives us confidence to move forward with our system simulations. We adjusted the drive level to the PA in order to give us an output power of 29.4 dBm. Now, we didn't randomly select 29.4 dBm as some sort of optimum power. It corresponds to a 6 dB back off from the 1 dB compression point. We had the PA model with the 130 milliamps per millimeter bias, and we observed the impact that this PA had on that constellation plot, the eye diagram, and the spectrum, and we calculated the EVM. Now, the EVM target for 256, we like 1.25%. I'm not saying if you go up to 1.5%, you'll fail. You won't. It's much higher than that. But 1.25% makes us feel really comfortable. That's a really nice, safe margin. And this is what we got. And we got 2.3%, so it's a bit higher than we want. But things to notice, can you see the eyes closing now? Particularly this one here. Really looks like someone who's had too many glasses of wine and stayed up too late. The constellation, it's not as neat. Things are starting to merge. And can you see how it's bent? That's a classic sign. And the spectral regrowth, it's really getting a bit close to us. Makes us a little bit nervous. So what we did now is to move to the 160 milliamps per millimeter bias, which we know through our circuit simulations gives us improved IP3. We adjusted the level into our PA, so we get an output power of 29.4 dBm. So we're comparing like with like, exactly the same output power. And now, what we see, the first thing to notice is we've got a nice healthy margin on the spectral regrowth here. That's good, that makes us feel more comfortable. The constellation plot is cleaner. You can see gaps between all the constellation points. It's not perfect, but it's never going to be. And the eyes, you can see clear gaps between all of these sampling instances. And the EVM is 1.3%, which is actually very good. You can receive QAM 256 modulation with a lot worse EVM than that. So, our simulations at 160 milliamp bias, we maintained the PM at 29.4 dBm, and it reduced the performance degradation compared to the 130 milliamps per millimeter. I mentioned these points on the last slide, but just to recap, the eye and constellation are much less corrupted. We've reduced the EVM to 1.3%, which is pretty close to our target of 1.25%. And this target, to be honest, is a very safe target. And the spectrum is well contained within the mask, a 7 dB margin. So a few conclusions. Gallium nitride is well suited to the realization of 15 gigahertz PAMMACs for point-to-point link applications. Now with that quarter micron process, in honesty, it's 18, 19 gigahertz. You can go up to that. If you want to go above that for all the other popular Ka band point-to-point link applications, you'll need a smaller geometry process. But GaN itself appears to be very well suited to this. We've highlighted the key steps in the design process. The PA itself, from a conventional microwave design metric, has good performance. At 28 volts bias, 130 milliamps per millimeter, we're seeing 22 dB of gain, an output power of 30 dBm at 3 dB compression, 36% PAE, and an output IP3 of 46 dBm, 46 dBm at 130 milliamps per millimeter. And if we tweak up the bias to 160 milliamps per millimeter, we see that increasing to 48.5. For communications applications, we need to operate the PA backed off from full compression, backed off to a sufficient level that it avoids modulation distortion. And we presented some system simulations to show that we can achieve the key performance metrics, the adjacent channel power, the EVM. For the QAM256 applications, we saw that the PA demonstrated a spectral mask that was within the ETSI limits, an EVM of 1.2%, and an output power at an output power of 29.4 dBm with the bias of 160 milliamps per millimeter. I think that's my last point. So.
Okay, thank you very much. Has anyone got any questions?
First, thank you, Liam, for a very enlightening presentation, and actually prepared the ground for my presentation. But I have a question. Did you actually measure EVM at 15 gigahertz, or you just simulated?
No, we've not made this IC yet. So
okay.
we have made GaN ICs,
right.
But because we're a design consultancy,
Right.
if we make something for someone, they're not always happy for us to stand up and tell everybody else what we've done, because they paid for that privilege. So this one's not yet been made.
Okay.
There's every possibility it may be manufactured, and I shall come back and tell you what we measured.
Okay, thank you.
Well, it's tantalising in your presentation is that you seem to be suggesting that for the same power capability, IP3, the gallium nitride actually has a better linearity, if I understand you correctly.
No, I'm not quite saying that. Right. It's not so much. I mean, gallium nitride can be a little bit more efficient, but the key thing is what I'm saying here is that for the same sort of for a much lower die area, you can get an improvement in IP3 using GaN compared to gas. That's really the message I'm trying to get over.
Because I mean, you did mention or hint at the fact that GaN, goes much more gently into compression, right, than gas. But I just wonder what there is in the technology that that allows it to be like that, or if that's not what you're saying.
No, it's not at all.
Okay, all right.
So the actual fact that GaN goes softly into compression can be something of a pain. It can catch the unwary person out. You need to take that into account. You also need a lot more work with your modelling. And again, I'm going to re-emphasize what Rob said earlier. You've got to get your modelling right. If your model's not right, you can design yourself a lovely circuit. When you make it, it'll be miles away. And the convention, there's a lot of work involved to get the model of the GaN transistor right, because that soft compression characteristic is a little bit different from all the conventional models that were originally developed for FET-based technologies and PHEMT-based technologies, which have a much sharper characteristic. But if let's take the leap of faith that the model does work well, then you can use gallium nitride to develop a die which has improved linearity and a much smaller die area than an incumbent gas part.
Okay, but I mean, what's the reason that it's much more gentle in going into compression? Is that something?
That's to do with the semiconductor physics. So I don't want to. It sounds like I'm portraying it as an advantage. It's not. It's actually a bit of a disadvantage. So it starts compressing, and it compresses and compresses. And, to really get it saturated, you might have to compress it 5-6 dB on a single stage. With a PHEMT process, you'd probably get it into saturation at 2-3 dB at the most. So that's not actually an advantage of GaN, that's a disadvantage.
Okay, but it is an aspect of the semiconductor.
Right, it's a feature of the technology, yeah.
I think it's just to add to the previous question. Is it in effect your P1 dB point is higher, so you're able to back off further to generate the same?
No, it's actually the other way around. Your P1 dB point is actually a little bit further away from your PSAT. And this is why I was taking particular point to mention about the size of the devices. Because if you size the devices of a multi-stage amplifier incorrectly, you'll make that even worse. And your P1 dB will be further away from your PSAT. And don't take my word for it. Look at some of the commercially available devices you can see. They can have P1 dB 6, 7 dB away from the PSAT. If you imagine you've got this soft compression characteristic that goes on for a long time, and then you've got the same on the input stage, but you've sized it too small. So it starts compressing here, and it goes on forever. And really, you can buy commercially available parts which require you to drive them 10 dB into saturation to meet the advertised PSAT.
Can you tell me the amount of gate current you were expecting? You mentioned that gate current was a potential issue with your layout.
It's not huge, to be honest, but as you drive it into compression, you do get more. It varies from process to process, and different foundries specify different amounts of gate current and then change it again when they get onto the release of a new process. And in honesty, if you've got a mature GaN process that is well designed, it's not hugely higher than a gas process. But when you're driving it hard, you might see maybe even as much as a milliamp per millimeter.
I've not got experience of Cree, but a company which I'd better not mention.
Yeah, they've improved, but go on. Yeah. It had a lot. Let me tell you what happened. Yeah. It had a lot higher gate leakage than that.
Yeah, particularly if you try to use the maximum drain voltage that the device is supposed to have. Yeah. So drain to gate could cause damage if you went too big on the drain and tried to get the most out of it.
And that particular company, I think, who we won't name, have a second generation of their process, which is much improved in that respect. But what it is, to some extent, you can almost think of it as the onset of breakdown, the onset of drain gate breakdown. And you really don't want the transistors to have too high a leakage current. It's a sign of a good process if the leakage current is nice and low. But nevertheless, when you've got a large amount of gate width on the device like that, that output stage could easily, when you're driving it hard, take perhaps 2 milliamps. And if you've got that 2 milliamps through a 1 kilo ohm resistor, you don't need to be a mathematical genius to work out that it's shifting that bias point around quite a lot. So that's why we try and keep it nice and low.
Thanks very much.
Okay, Terry.
I'm going to mention a specific company.
Thanks, Terry.
Yeah, there's one over west called stands for 3 something. I think we all know who that is, but well, Triquint was. Triquint had quite recently announced low noise amplifiers in GaN technology. I appreciate this is something a bit adrift from the main theme of your talk, Liam, but do you have an opinion on the likely take-up of both power and low noise in this technology?
I have an opinion on everything, Terry. Thanks for asking. Yeah. So what GaN isn't fantastic for noise, but it's not a disaster either. So what people do with these LNAs, and they call them robust LNAs, and they're pretty nice parts, those Triquint parts. So you bias them at sort of 10 to 15 volts. The knee voltage in GaN is around about the 5 volt level, so you can't go too low. You bias them at 10, 15 volts rather than the 28 volts or even 40 volts you would for a PA. And the big benefit to them is that they can withstand a lot of input power. So you can either do without a limiter or do with a much lower power limiter, which has lower insertion loss. So you end up with a smaller system, potentially a slightly cheaper system, and what you're trading is a slightly higher noise LNA for a reduced performance limiter.
Got you. Thank you. Thank you.
Okay, thank you. Thank you very much, Terry.